Hello.
Hello. We can wait till 8:05 and then we can start.
Cool.
Yeah, so let you know that we have some future events coming on, and we welcome people to join. On October 10th, we will have a talk, some invited talks at AMD Advancing AI, and then on October 16th, there'll be an online meetup co-hosted by SGLang, FlashInfer, and LMSYS, and the three projects are collaborating closely, and we'll have more technical details about the features in SGLang and FlashInfer and LMSYS. You're all welcome to join, and the link is on SGLang GitHub repo. And we also have some future events which are still to be done, but keep an eye on it and stay tuned. So in the first part, we'll still have Leming to briefly talk about Q4 planning because some people may just join the first time, and then we can talk about some our current focus and some in progress features, and then call for beta users for the new features. And then Andy will talk about this new work about double sparsity, which is a technique that can use for accelerating long context inference. So let's go. I cannot hear you, Leming.
Okay, yeah. Hi.
Good.
Okay, maybe, yeah, we can get started. So let me share my screen. Share the window. Okay. So in the last meeting, we went through a lot of items we want to push for this quarter, and a lot of them we already have some prototype for a lot of them. I guess the most important item right now is to further reduce the CPU overhead. So during the last week, we pushed a lot of refactor to refactor the code base to make it easier to hide the overhead of CPU. So specifically, there is this PR basically is a very important PR. So basically, we want to separate the basic. Right now, we have a scheduler and a GPU worker inside a single process. But later, we probably want to use multiple processes to overlap them. And this PR basically defines the protocols between like the two processes. So we will have schedule batch, which includes all the CPU schedule information, and forward batch, which includes all the GPU information. And then we also have a model worker batch, basically encodes the intermediate things that will be transferred from CPU to GPU. And then this PR basically is a very important step towards this refactor. And now everything will be much cleaner, and the model worker batch is only interface between CPU and GPU. And later, we will make this class minimal and clean, and then make the communication between two processes much easier. Yeah, so this is a progress on CPU overhead hiding. And then we're also working on a lot of new models. So for example, Llama 3.2 multimodal model and the Quam 2 VL model. We all have working in progress PR to support them. So this is for the model coverage. And the Villa, we also have some collaborators from NVIDIA working on adding support for these vision language models. And then besides this, we also added the interface for reward model. So this is for reinforcement learning and ILHF. So now you can load some reward model, and we have new endpoints to compute the score or classify the sentence. Okay, so this is on the model coverage. And LoRa support, yeah, we also have some ongoing PR to optimize the LoRa performance. Yeah, I think that's pretty much it, because I already went over the list last week. So I guess maybe if people have any feedback or want to prioritize any item, now this is time for us to discuss. Do you have any people? Do you want to prioritize any items?
Or if you have anything later, if you have anything want to point out, you can just add as a comments under this roadmap issue.
Yeah, and okay, last thing about I want to mention is quantization. So we also discussed a lot with Xiao and Ke about what kind of quantization library and format we want to use. So right now, like there are a few candidates, and because Hai works on like one quantization library from AMD, so we will probably try to integrate that quantization library, and that should like provide both FP8 weight and FP8 KV cache quantization for like static quantization.
And also, if you want to hear more details about like the CPU overhead hiding and also like JSON constraint decoding, fast JSON decoding, and we'll have something new from MLC which will be like integrating to SGLang later. All the details about those techniques, you can expect them in the online meetup, which is on October 16.
Yeah, sounds good. That's pretty much from the roadmap side. Yeah, and if you want to work on any item, you can post on the general channel or direct message us. We can provide you some guidance on how to get started on any of the items. Okay, thank you. Let me turn off the...
We can move to Andy's talk.
Okay, I will share the screen. Can you see the screen now?
Yeah.
Okay. Hello everyone. My name is Shuoyang, and you can just call me Andy. I'm a first-year student from Berkeley Skylab, and my advisor is Professor Jan Stoica. Today, I'm really happy to share with you my recent work, double sparsity, and its integration into SGLang. There are three main parts in my presentation today. In the first part, I will give a brief introduction to double sparsity. Then I will discuss some details about the integration of double sparsity. And finally, I want to share some thoughts on the future work of double sparsity and its integration to SGLang. Well, let's begin with the first section. So maybe you are wondering, what is double sparsity? To briefly summarize, double sparsity is a sparse attention technique that aims to accelerate the long context inference. So in the first part, I would like to provide some backgrounds on the long context inference and sparse attention. We all know that the long context is a hot topic today, and almost all models, whether they are open sourced or closed sourced, they are supporting context length over 128,000. For example, the Llama 3.1 model with 8 billion parameter, they have 128 context lengths, and the recently popular GPT-01 model, they have even longer chain of thought. However, this extremely long context comes at a significant cost in speed. The primary reason for this slowdown is that long context inference is severely memory bounded. For example, serving 16 requests of 8,000 lengths with a Llama 7B model, the total memory access require 44 milliseconds within a single decoding step, which accounts for more than 80% of the total serving time. Some people have tested the GPT-01 with the last question from the college entrance exam, and the chain of thought part took over 102,000 to complete. Actually, it's okay for a high school student to finish it within 2 minutes, but actually we want faster from GPT, right? So this growing importance asks the researcher to speed up the attention in the long context inference part. And that's why we propose double sparsity. The goal for the sparse attention is to reduce the access to the KV cache during the decoding part, and making the attention computation more bandwidth efficient and have the overall speed up. So there are two main observations that leads to double sparsity. One observation is that not every token is equally important for the decoding. We call it token sparsity. And another observation is that during the calculation of activations, only a small subset of features channels significantly influence the final output. And we call it channel sparsity. Previous work have utilized the token sparsity and the channel sparsity separately. For example, the heavy hitter oracle, H2O, it employs a dynamic strategy that maintains a small fixed size cache of important tokens during the decoding step. However, due to its limited size, it must evict tokens during these steps. And once the tokens are evicted, these tokens cannot be recovered, right? And it will significantly degrade the accuracy. And so we proposed the double sparsity, a method that can leverage two kinds of sparsity together. We retain all the tokens and we compute the attention only over the important tokens. So the most important part is how can we find those important tokens? And that's why channel sparsity can help us to determine which tokens are important. Channel sparsity can estimate the importance of tokens at runtime using heavy channel embeddings, because only those heavy channel, important channels, they really matters in the decoding. So we only use them to predict those important tokens. Our key insight is that while token sparsity is highly dynamic, the channel sparsity is rather static. And we can use those static channel sparsity to predict those dynamic important tokens. And the core design, there are 5 parts in the core design. Before decoding, we need to determine those important channels. And we can use the offline calibration set to predetermine those channels. And when we are doing the decoding part, there are 4 steps. The first step is to store those important channels value in label cache. And we will going to talk about what is label cache. And once we have the important channels value, we can compute the approximate attention on those important values. And based on the approximate attention, we can select the top K tokens. And with the top K tokens, we can just compute the attention over the top K tokens, just like previous sparse attention techniques. To identify the channels that have significant impact on attention, we should conduct an analysis of each layer's channel using the pile validation dataset. And we can focus on their contribution to the final attention output. Once we use the validation set to offline calibrate those channels, we measure their importance, and we got the important channels index. And after identifying those outlier channel or important channels index, it's important to assess them efficiently. For example, if the index is like 1, 3, 5, 7, and those index are not contiguous, we need to read those channels directly from key cache, and this can lead to non-contiguous memory access. And it will waste much memory bandwidth. So we want to alleviate those non-contiguous memory access. We leverage a label cache to store the predetermined heavy channels values. Once we got the heavy channels index, we store those values in a compact label cache. The cache is much smaller than the original key cache. And with the fixed label cache, we can compute the approximate attention with the label cache. And since the index in the label cache are contiguous, we can directly read those important channels value from the contiguous label cache. And we don't need to retrieve the non-contiguous segments from the key cache. And I would like to give an overview of the double sparsity algorithm, which includes label cache initialization in the prefilling stage and the sparse attention sparse attention in the decoding stage. During the prefilling stage, all heavy channel values from the key cache are stored in the label cache, and we initialize the label cache. And in the decoding stage, we store despite the new key value, we also add the new label, which is extracted from the key, and we add a new label to the label cache. And based on the approximate attention, we can select those top K tokens. Then we compute the attention on the top K tokens, similar to previous sparse attention techniques. And in this figure, we can see the top K, the K is 3 here. And we compute the softmax based on the top 3 tokens. And the top 3 tokens come from the top K approximate attention weights. And with this method, we can reduce the total memory access and with nearly no loss. So we have to evaluate the effectiveness of our method. We demonstrate that double sparsity algorithm can maintain robust performance with a sparsity setting of 1/16 across various benchmarks, including Wiki2 perplexity and long context benchmarks and key value retrieval benchmarks. We can see that double sparsity significantly outperforms other post-training sparse attention techniques. The green line is double sparsity, and the higher is better. We compare it with the newest Quest algorithm, the previous heavy hitter algorithm, the streaming LM algorithm, and we can see with the same token budget, double sparsity is way better than other sparse attention techniques. And we need to demonstrate double sparsity can achieve real speed up. We select Llama 7B model as a base model, and we focus on high workload scenarios to push the limit of double sparsity. The context length is from 4,000 to 16,000. And we can see each case achieve at least a 5 times speed up. And in the end-to-end scenario, there's a 2 times speed up. And this figure is about the attention speed up. And we can achieve a 14 or even 16 times speed up in the attention operator. So with this 2 figure, we can demonstrate that we can achieve a really high speed up with nearly no loss. So
could you explain more on why double sparsity gets the good accuracy, but the other baselines cannot?
That is because, for example, the heavy hitter, it will evict those so-called unimportant tokens. And those unimportant tokens may be important in the future. So if you just evict those tokens, the accuracy will degrade, and it's simple to understand. But the Quest use block sparse attention. It used the max representation and the mean representation of each token block or token page. And it's not that fine-grained as double sparsity, because double sparsity's page size is 1 token per page. And Quest needs 16 or even 32 tokens per page. It's not that fine-grained. That's the first part. And the second part is it doesn't utilize the channel sparsity. So it cannot retrieve those important tokens as accurate as double sparsity. So within the same token budget, double sparsity can retrieve more accurate tokens, and it can achieve a higher score.
Okay, good.
Okay, so yeah, now let's move to the second part of my presentation. I would like to share some details about integrating double sparsity into SGLang. I think this part can help the developers to know how to integrate a new technique into SGLang. As a developer, I think SGLang is really developer friendly because its abstraction is really good, and I can reuse much of the code, and it can speed up my development process. So I think the most critical part of integrating double sparsity is how it can be combined with page attention. This includes three key elements. First, we need a label cache. We need a label cache in addition to the original key value cache, right? And the decoding algorithm, the attention algorithm is slightly different from the original one. So we need to support the page approximate attention. And most importantly, we need to reduce the metadata size. We need to help the label cache and the KV cache to share the same mapping. So we don't need to add new metadata to the original input metadata, right? So for the label cache part, I just set up a separate label cache in addition to the original KV cache. And both the KV cache and the label cache share exactly the same layout. We can see in the right part. The greatest difference between the key value cache and the label cache is their size. Because the label cache only stores the important channels of each token. So the label cache size is smaller than the KV cache, but with the same mapping, you can retrieve the correct token from the KV cache, and you can retrieve the correct label from the label cache with the same mapping. And the code is in the left part, and we can see it's exactly the same despite the head dimension and the heavy channel none part. And this code can be reused from the base token pool, base token KV cache pool. And this part is quite easy.
So when you estimate the memory pool that we can use, did you also count in this the memory consumed by label cache?
Yeah. But it only takes 1/16 of the overall memory. So it's not a burden because you can achieve a 16 times speed up with only a little bit more memory. So I think this process is it won't give high burden to the overall throughput, right?
Yeah, I also have a question about this figure. What does this two-dimensional figure mean?
Actually, there's no two dimensions. It's just a KV pool. It's one dimension. But I just want to illustrate the KV cache, and I want to show that they can share exactly the same mapping, and we don't need to add more input metadata to continue the decoding forward. We don't need to add more metadata. I want to share this point. Yeah.
I see. Yeah, probably you can make it one dimension and you can use two columns to represent that.
Yeah, sure. Maybe if actually one dimension is more clear. It's more clear. Yeah. And once we implement the label cache pool, we need to finish the double sparsity decode attention, right? And this approach is divided into 3 steps we just mentioned before. The first step is to compute the approximate attention. this process is really similar to the traditional page attention, but it only focuses on the product of Q and K, because we only need the Q and K to get the approximate attention weight. And after we obtain the approximate attention output, we can use the top K, we can use torch top K to filter and identify those corresponding index using the same mapping. Because it relies on the request to tokens index, we can use the top K token index, and we gather those index from the original mapping, and we got a new request to token top K index, and we can just transfer the new mapping to the original page attention. And the third step is exactly the same as the original page attention, but it has more mapping. And this process is really easy. We need finishing this code is really easy, because we can reuse much code from the original SGLang. We only need to modify the first approximate attention part and the third part, and we can use this. We can integrate this to the attention backend. And thanks to the attention backend abstraction, this process, we need to only modify 2 kernels, and this process can be integrated to the SGLang.
Is it double sparsity a new backend called double sparsity backend?
Yeah. It's a new backend. We call it double sparsity backend, but the code can be reused, and we can just you can just use enable double sparsity to start this backend, and there's no conflict with other techniques. Maybe you can use other. I haven't tried it, but I will try. I think it's compatible with other techniques. It actually is free launch for long context inference. Yeah.
Okay.
Yeah. Sorry, I have some questions about this. So, so I think right now this is not compatible with CUDA graph, right? Is it because of some of the operation here, or it's because something else?
Yeah. Because this can be the CUDA graph part can be fixed. I didn't try it, but I think it can be. I didn't implement the CUDA graph initialization, and if I initialize the CUDA graph part, I think this part is compatible with CUDA graph. Yeah, I only finished the double sparsity decoding part, and since for each attention backend you need another CUDA graph initialization, right? And so I only finished the double sparsity forward part, and if I finish the attention backends CUDA graph initialization, I think they are compatible. Yeah.
Okay, and we have a question from the audience.
Okay. Will top K? Actually, the top K is
are you asking top K as the label cache, or is say the top K sparsity is too expensive?
I think he is referring to the top K in this code, because we have to run top K here.
Actually, the top K is really cheap here. Actually the most expensive part is still the third part, because we need a softmax in the full attention. But in the first step, we only need a GMV, right? And this part is really fast. Although it still needs some memory access, but actually it's way faster than the third step. And the top K part is also really fast. It won't damage the overall speed up. Yeah, the top K is really cheap here. Yeah, but actually this actually compared to the 128,000 context lengths, the top K is way cheaper than the memory access. Yeah, because this part can be done concurrently. Actually, I don't think this part is expensive. You mean the top K operator? I think this part is really cheap because in the end-to-end experiments and in the end-to-end, actually Quest has the top K here because it has to retrieve the page from all the memory page.
Yeah, Hanshi is saying that Quest has less number of top K tokens. Did you have any early benchmark result for this part? Oh, I guess Andy actually already compared the double Sparsity with Quest in the paper. So, and because the Quest has a significant accuracy degradation, so and the double Sparsity actually has a significant advantage on that we can achieve a lower sparsity level. But I'm not sure if you have any result comparing double sparsity with a lower sparsity and the Quest with higher sparsity, the speed up comparison. Like if they achieve the same accuracy, which one is faster? Did you have any kind of experiment like that? Maybe. So for example, double sparsity with sparsity 1/16 and Quest using sparsity 1/8 or 1/4, and they achieve the similar accuracy, then how to compare their speed up? Is double sparsity still, I mean, I don't know, if they are the same sparsity, which one is faster? Do you ever compare that?
For now, actually, the Quest only supports the single batch. It doesn't support batch size 2, or even it also doesn't support the serving because the page is not that fine grained as double sparsity. Double sparsity's page size is 1, and the Quest is 16, and actually, they just want to remove the page part. So I believe I know the author of Quest really well, and they really want to remove the page design. So I think maybe we should just abandon the page. Yeah, we can just abandon the page and the 16 times for the top K operator, because the top K operator is small and it's really cheap. So I think it won't destroy the performance of double sparsity. Yeah.
There are 2 more questions from Hai and Chong.
Let me go first. Sorry. Yeah, I'm trying to understand the theory behind it. So I think you said, cool, using the important token. I don't know, I should have read your paper, but not yet. I'm thinking, how do we think of the case that every decoding step, it depends on the history, how do we consume the idea at different decoding position, your important token, you look at, they will have good overlap or totally irrelevant?
I understand your question. You are asking that in different decoding steps, are those tokens varies a lot? Are those important tokens various, right? You are asking this. Yeah. And I think that's why I think it varies a lot, because we have different performance in each benchmark. For example, if you can reach, if those important tokens are exactly the same, then I think the heavy hitter oracle should should perform better or perform equally just as double sparsity. But actually with lower budgets, the performance degrade, which means it just evict or discard those so-called unimportant tokens, and those unimportant tokens become more important in the later decoding step, right?
Yeah.
And we have tried with multi-round retrieval, key value retrieval, and we can give two questions about we can give two questions. One question is ask key 1, and another question is ask key 2. And for the key 1 decoding, and it will maybe the focus is about the key 1 value 1 part, and the key 2 refers to the key 2 value 2 part, and we can create those kind of benchmarks to make the important tokens varied, right? So it's quite common that the decoding tokens, sometimes they are important, sometimes they are not.
Okay,
So
thank you. Good question.
The key observation here is that when some token was not important at the beginning, it could become important later.
Yeah.
And throughout the whole decoding steps, it actually changed a lot, right?
Yeah.
Yeah, I guess so. So, of course, I go back to read your paper. It's great work.
Thanks.
Thanks for the answer here.
And Chong?
Yes. Yeah. First of all, thanks for the great work. I have a slightly more general question. So for this specific case, I'm pretty convinced that this top K operation isn't that expensive. But
Yeah.
for a general case, let's say that we want to quantitatively understand the cost of a certain operation. How can we do that in SGLang? So maybe this is more like a question for the authors of the framework. Like, how is there like some kind of like a runbook or tutorial where the users can hook up some kind of a profiling tool, for example, LMSYS, to SGLang such that we can get a detailed like very breakdown like a timing analysis of all the operations?
Yeah, this is a really good question. And for the SGLang part, I think we can use LMSYS system to profile. We can profile the approximate attention part, we can profile the top K selection part, and we can profile the final attention output part, right? And I think because I have done this in the GPT fast code, and I haven't done this in the SGLang code, and I think this really matters, and because the overall speed up and each part, how much time each part take, it depends on the workload itself. For example, some workloads, they are extremely long, and the attention part is really long, and maybe there's some difference. And if they are just so-so, there are maybe 8,000 tokens or 16,000 tokens, not 128,000 tokens. Maybe the matmul part, the gem part is more important. So it depends on the workload. But I think the LMSYS system can help you to identify which part is expensive and which part is not that expensive.
Okay, got it. Yeah, thank you. And I just saw that Ying shared a link in the chat, in the channel. Yeah, thanks so much for that too. And another, just to follow up, I understand that SGLang uses flash infer as some kind of backbone, right, backhand. And to which extent can we do this kind of profiling? I guess maybe put another way, like to kind of what level of operation that SGLang just like hand over to flash infer, and we can no longer do kind of profiling using the method that is described in the link.
I think for me,
Yeah,
like
maybe I can answer better. So I don't know whether you have used the LMSYS before. So basically, flash infer is just like 1 or 2 kernels. We use that, and then if you run LMSYS, then flash infer is just one kernel, and like everything you can see, because NSide only profile from kernel level. So like NSide doesn't distinguish flash infer or PyTorch or SGLang. Everything are just CUDA kernels. So they will show you like a flattened kernel view.
Oh, I see. Yeah, that makes sense. Okay, yeah, thank you.
I also tried PyTorch profiler before. It can show you maybe not that accurate, but actually, but could be a more readable format for including the CPU time, and it can tell you when you launch the kernel and how long you spend on the kernel.
I see. Yeah,
so both two tools can be used to analyze the performance.
Yeah, thank you.
And I think maybe I will talk about
and you got one more
yeah.
question in the channel in the chat.
Okay. Actually, I just used the long bench output. The long bench output score, and it's aligned with the Quest table itself. So it's exactly the same. It's exactly the same as the long bench output. I used exactly the same measuring method as Quest. So I think maybe you can refer to the long bench evaluation. Yeah. Hi.
Do we have time for more questions, Ian?
I think so. Yeah.
Okay. Yeah, quick. I sorry, take time. So, can you analyze why you think? I know the motivation, but there's sometimes the decoding output might be depending on a lot of small probability tokens, right? Let's say you have very long sequence, and let's say you have 1,000 very low probability tokens from input. Really, they work together. Actually, they work together to compute one bigger probability token to detect the output. Is that wrong thinking, or what do you take there? Yeah.
Actually, I know what you mean. You mean maybe the small probability token, they also matters. But actually, I think it's not that correct, because the softmax function is a kind of max function, and the max function can only identify those important tokens. But it's softmax, so it can look at more tokens rather than one token. And actually, it's the softmax function's feature. It's quality to look at several tokens instead of looking at all the tokens.
Mm-hmm. Yeah. So if you combine one token with small probability, it might not count. But maybe there's very many together. These smaller probability tokens, they have high synergy or some sort of and they. Okay, but the softmax also, it has like temperature kind of thing concept there, right? So yeah. Yeah. I don't know. I'm just asking you this. Sorry for that. Yeah. Okay. Yeah.
Yeah, it's actually it's the foundation of sparse attention. Most sparse attention techniques, they only utilize the token sparsity feature. And relying only several tokens, it can successfully decode the next token. And that's how most sparse attention techniques work. And I think there might be some cases the small tokens, the less important tokens, they combine together and they are important. But for now, we didn't have a benchmark like this to maybe see the importance of those less important tokens. Maybe if we have a benchmark to, we can see these tokens really matters, and maybe this techniques should be updated, right?
Yeah. Okay. Maybe we can discuss offline in the interest of time. Thank you.
That's cool. Thanks.
Yeah.
So what's the
Okay. So maybe there are several steps. So one thing is, let me just mention, I need to combine the CUDA graph or torsion compile with the double sparsity, and the approximate attention part is low bit. So maybe we can use low bit tensor cores to finish the approximate attention instead of scaling and dequantize. These are two easy parts. And there's one difficult part. It's also mentioned in the double sparsity paper. It's called double sparsity offload. Since the embeddings between layers, they are quite similar. So we want to reduce the memory footprint of the decoding process. Actually, we can use the previous layer's embedding to predict next layer's important tokens. And when we are computing the attention and netmore in the previous layer, we can prefetch the next layer's important tokens. And the experiment in the double sparsity paper shows that it can also achieve a really high accuracy. So double sparsity offload method may be integrated to SGLang, and we can reduce the memory footprint, or we can serve a large model in a single card with severe memory constraint. And these three parts are potential future work for me. Yeah.
How long do you expect to take for merging the PR?
Maybe 1 week. Maybe 1 week to finish the
current one.
I think 1 week for the CUDA graph, because I didn't implement the CUDA graph. Yeah.
Okay. I think we can merge the major thing first, and do the optimization later, like offload the CUDA graph.
Maybe next week I can wrap up those kernels. Yeah.
Yeah, exactly. Because we will do a lot of refactoring. So if you merge your code earlier and we add a CI to protect that, that will make your future rebase easier.
Okay.
Yeah,
sure.
Yeah.
And thanks. That's all my presentation. And thanks, Lianmin and Ying. Yeah. Thanks for your help.
Yeah, thank you a lot. Is that mostly that's the most thing for today? We can if we have question, we can take one more, or we can briefly talk about what we want to focus in next week from development side. So, Lianmin, what do you think? What will be the focus of next week, or before next public meeting, like 2 weeks from now? If you can wrap up the CPU overlap and also double sparsity basic functionality, and also add that speed up for LoRa adapters.
Yeah, this will be the focus. I guess for me, the major focus is to further reduce the CPU overhead, and we can expect something between 20 to 40% improvement.
Cool. Yeah, Zhuohao shared the paper in the channel. Yeah, I guess this meeting will end at 9 p.m. So if we don't have more questions, we can answer earlier, and like Andy and Zhuohao, we can talk more about that offline. Cool. So that's actually all for today. Let me raise who raised the hand.
I just want to
Okay.
add some emoji.
Okay. Thank you. Thank you, everyone.
Bye.
Yeah. Bye.